Okay, after finding the value for Kc, knowing about the equilibrium, it's time to play with Kc a little bit. We can use it in different ways. Kc, depending on the magnitude of Kc, we can determine the component of the system. Also, we can tell like where the direction of the reaction. So let's work on the equilibrium the composition. When Kc, when the amount of Kc, the value of Kc is more than 100, then it means that the reaction is going good towards the product. So reaction mixture or equilibrium mixture is mostly products. When you have a high value for Kc. When Kc is very small, is less than 10 to negative 2, then you can tell that equilibrium mixture is mostly, I'm sure you would say it's mostly reactants. Oops. And then if Kc is almost 1, approaches the value 1, then you have both of the components in the mixture almost equal. I mean, you have, let's not use the word equal, both reactants and products in the mixture. So let's work on an example to make it more clear. On slide number 42, it says Kc for a reaction is 0.82. Describe the composition of the equilibrium mixture. So this value is closer to 1, right? It's much smaller than 100. It's higher than 0.01. So it's going to be, you will have both substantial amounts of both reactants and products. That's how you determine the composition of the equilibrium based on the value for equilibrium constant. The next application of value for Kc is this. Let me give you this very simple example. Let's say Kc is here. Okay? Kc is the equilibrium system and is here. Let me introduce you to a term. It's called Q, or reaction quotient. Reaction quotient. What is the difference between Q or QC and Kc? Q is the same, like the equilibrium constant is the same form, let's say the ratio of products over reactants, but you use initial concentrations for its value, not the equilibrium concentrations. So Q, when you determine it, the value can be less than Kc, can be more than Kc, can be equal to Kc. So what does that mean? Again, we're working with a reaction in equilibrium form, and Kc is C D divided by A. Okay? Now, let's say in a question you have determined K I mean, you have determined Q and you are given the value of a Kc. When Kc value is more than Q, means your Q is here, right? You still have to have reaction going on to reach to Kc, right? So reaction hasn't reached equilibrium yet. This is equilibrium where you can determine Kc, right? Because Kc works with the equilibrium concentrations of products and reactants, right? You did an example on that. But for Q, you use the same equation. Instead of equilibrium concentrations, you can use concentrations at any time. And we will work on a question, on an example. So Q is a measure of where you are standing. Have you reached equilibrium? Have you passed equilibrium? Or you are at equilibrium? So how do you determine it? By comparing it to the value of Kc. If Kc is still larger than Q, means you still haven't reached equilibrium. So what happens when the system hasn't reached equilibrium yet? It has to proceed to go more towards products, right? So the reaction proceeds to right. Because it still has to form more products than coming back. When Kc is less than Q, means you are here. You already passed the equilibrium, so the reaction starts going back towards the reactant. So reaction proceeds to left. And when Kc and Q are almost the same, then reaction is at what? Equilibrium. It's time to work on an example, right? Let's say I'm working on the example on slide 46. Nickel oxide can be reduced. Nickel oxide can be reduced to carbon dioxide if the partial pressure of carbon monoxide is 100 millimeters of mercury and the total pressure of carbon monoxide and carbon dioxide does not exceed 1 atmosphere, will this reaction occur at 1500 Kelvin at equilibrium? Kp is 700 and temperature is 1500 Kelvin. We want to see if the reaction moves forward or backward. So pressure of carbon monoxide is given as 100. Pressure of carbon monoxide and carbon dioxide total is not going to be more than 1 atmosphere. Since this pressure is in millimeters of mercury, let's change this one to millimeters of mercury also. You know that 1 atmosphere is 760 millimeters of mercury. So, can I say the pressure of carbon monoxide plus carbon dioxide does not exceed 760. They are both almost 760. So if 100 is from carbon monoxide, the pressure of carbon dioxide is going to be almost 660 millimeters of mercury, right? Because the total should be 760. Now, how do you write QP? QP, we said, is written as the same as Kc or Kp. Here Kp is given, so let's work on Qp since you have two gaseous components. You remember we do not write anything, any concentrations or pressures for solids, because solids, first of all, they don't have a pressure, and then if you want to work with the concentrations will be equal to 1. So Kp is going to be written as pressure of carbon dioxide. There is no coefficient, so the exponent is 1. Here, P of carbon monoxide. So what was the pressure of carbon dioxide you found? 660. And pressure of carbon monoxide is 100. It's going to be how much? 6.60. That's your Qp. So now let's compare. Qp is 6.60 and Kp is what? 700. Have we reached equilibrium yet? No, not at all. We are far away from equilibrium because for equilibrium Kp is 700, but we still have 6.60. So the reaction still needs to move forward. I hope you understood. We calculated Qp one more time. The concentrations or the pressures you have for Qp can be at any time in the reaction, but for Kp and Kc, it's only you're working with the equilibrium concentrations and pressures. So Q is a measure of where we're standing. What is the situation? All right. Now you learn about Q. It's time to work on some more examples of when we have Kc, then finding the concentration. So far we worked with the concentrations, we found Kc. Now let's use Kc to find the concentrations. The same method, nitrogen plus oxygen is going to give you 2 nitrogen monoxide gas. If an equilibrium mixture at 25 degrees Celsius contains 0.4 molar of N2, 0.040 molar of N2. I'm writing the concentrations underneath. And 0.010 molar of O2. What is the concentration of NO in this mixture? The equilibrium constant is given at this temperature, which is 1 times 10 to negative 30. How do you write Kc for this equation? It's the molar concentration of NO squared because of the coefficient times N2, and we are careful, all of them are gases, so we can't write it. So we are solving for NO. So 1 times 10 to negative 30 is NO squared divided by what is the concentration at equilibrium? 0.040 times 0.010. So get the second root from NO, so you will end up having 2 times 10 to negative 17 molar. So you multiply these, and then you will end up having the square root, and then you get the square root. So molar concentration at equilibrium is going to be 2 times 10 to negative 17. Don't worry about the negative, the small number. You might say it's a very small number. Yes, because your equilibrium constant is very small. Means that this reaction happens really slowly. So that's one of the examples of how to work with Kc and find the concentrations. Also, if you have initial concentration and value of Kc, then we can build the ice chart, initial, change, and equilibrium. And we will find the equilibrium concentrations. We have different types. We work on slide number 51. It says hydrogen iodide, 2Hi. Decomposes to hydrogen, and iodide at 800 Kelvin. The equilibrium constant Kc is equal to 0.016. If 0.50 moles of Hi is placed in a 5-liter flask, what will be the composition of equilibrium mixture in molarities? So, since we need the concentrations in molarities, instead of building our ice chart in moles, let's use the molarities. So let's change 0.5 to the molarity. 0.50 divided by 5 liters. So it's going to be 0.10 molar. Now, instead of 0.5 molar, let's use 0.5 mole. Let's use 0.10 molar. So we can build our ice table with moles. If you need the molarity, because so far all the liters, all the volumes were 1. So moles and molarity was the same because you were dividing by 1. But here, the volume is not 1, so molarity will be different. Now, you change it to molarity, everything else comes up as molarity. Let's build the ice chart. At the beginning, everything will be 0 on the product side. Then, the coefficient is 2. So minus 2x will be deducted. And the coefficients are 1 and 1. X and x will be added to hydrogen and iodine. At the end, you will have 0.10 minus 2x, x, and x when you add these two. Alright? Now, you have nothing else but your Kc. So let's put the value of Kc 0.016. The value of I2 times H2, which is x squared, right? X times x. Can I put x squared? Divided by 0.10 minus 2x. And isn't it squared again? Because of the 2. Alright. So, now, you see the right side is a perfect square, so you can get the square root from both sides. Then you will end up having the square root, get this, you get this, so you will end up having 0.126, 0.126 is equal to x divided by 0.10 minus 2x. And then if you do the cross multiplication and clean it off, x is going to be how much? 0.010 molar. Okay? So that was x. What are x? The concentration of H2 and I2, right? Which are 0.10 molar. Then concentration for Hi was how much? 0.10 minus 2x is 0.10 minus 2 times 0.010, which is going to be 0.08 molar. That's the composition of the mixture at equilibrium. Now, you were lucky having the perfect square on both sides, but what happens if you don't have the perfect square? Then you need to go with rearranging a quadratic equation. That's the longest form. I don't call it hardest. This is the longest form of this type of questions you may have. But no worries, we all know what is a quadratic equation. A quadratic equation is in the form of ax squared plus bx plus c. Just refreshing our memory from school days. So x is going to be minus b plus minus b squared minus 4ac divided by 2a. And it gives us two roots. One of them is always not acceptable, and we pick the other one. Ready? Let's work on the question on your slide 56. N2O4, the gaseous form, will change to 2NO2. At 100 degrees Celsius, Kc is 0.36. If 1 liter flask, we have a 1 liter flask, so our moles or molarities are the same. The flask initially contains 0.100 molar of N2O4. What will be the equilibrium concentration of NO2? Okay, at the beginning, we're building our ice table. Whenever we talk about equilibrium, we need our ice table. At the beginning, we have 0.1 molar of N2O4, and how much of the product at the very beginning? Nothing, right? By proceeding, when the process, the equilibrium goes through the change, the reaction goes through the change, something called X will be deducted. The coefficient is 1 here. But 2x will be added to NO2. At the end, we have 0.0100 minus x and 2x here. So if you write the Kc is going to be 2x squared divided by 0.00 minus x, which is equal to 0.36. That's the value of Kc, right? Now, let's write it in a form and organize it in the form of a quadratic equation, because the left side is not a perfect square. You cannot do the same thing you did in the previous example. So we will do the quadratic equation, 4x squared, and then now multiply this side. It's going to be plus 0.36x minus 0.036. This is a form of a quadratic equation. Ax squared plus bx plus bx plus c. All right? So, what is b? This. What is c? This guy. So, x is minus b, minus 0.36 plus minus 0.36 squared minus 4ac, which will, let me just, 4ac. 4a and minus c is a negative number. Divided by 2a is 8, correct? Now, if you find the values, x is going to be because we have plus and minus, we have two values, 0.06, or we will have minus 0.15. X is supposed to be a concentration. Do we have a negative concentration? Nope. So we pick the first one. Now, the question is asking for the equilibrium concentration of NO2, which is 2x. So the equilibrium concentration of NO2 is going to be 0.112 molar. That was the longest. You see, this is not hard, but that's the longest. You can work on the next example of it's almost the same, but it's a perfect square, so you're lucky. Okay. Work on different examples. In the next video, I will be talking about Le Chatelier's principle, and we try to wrap up this chapter.